It's time for our last keynote. It's on the theme, Communications Perspective on Digital Privacy. So many of the activities in cyberspace, from social networking to the use of mobile apps, leave digital footprints that could compromise the user's privacy. In this talk, Elza Erkip focuses on de-anonymization attacks, where publicly and privately available information about users are leveraged to compromise user identities. What's the likelihood that users in cyberspace can be uniquely identified from their activities? And how could you quantify such risks? Professor Erkip is an institute professor in the Electrical and Computer Engineering Department at New York University Tandon School of Engineering, and her research interests include information theory, communications theory, and wireless communication. And it's a pleasure to welcome you, Professor Erkip. Welcome to our conference.
Thank you so much. It's great to be there virtually.
What's your view from where you are sitting now?
Oh, I'm seeing downtown Brooklyn. It's a nice, bright and sunny day.
That's nice. We also have a bright, sunny day here in Stockholm. I'll leave the stage for you. We have a lot of questions always following our keynote speakers. So leave time at the end and I'll take those questions with you.
Certainly. Thank you.
Thank you again.
Okay. Good afternoon, everyone. Good morning for me. It's great to be there virtually, not in AR form in 2D, but nevertheless, it's great to be speaking to you. I'm just first kind of a quick background on me. So I'm in the Electrical and Computer Engineering Department at NYU Tandon School of Engineering. I'm also a member of NYU Wireless, where we work with the wireless industry to design future generations of networks. So certainly the previous panel was very much close to some of the things that we're looking at NYU. My own research group focuses on the theoretical foundations of networks. We do look at wireless networks and think about future wireless networks, but we also are interested in social networks mainly from the perspective of privacy. And that's what I'm going to talk to you today. When we think about social network privacy, we can think of a social network as a graph representing user connectivity. And we all know that data from these social networks are made available for research purposes as well as for commercial purposes. And oftentimes, in order to protect user anonymity, the identities of users are removed. Now, we may be wondering, are anonymized data truly private? Now, as you can guess, the answer is a big no. And we see, articles every day in popular press. One of them is about a recent article on Joe Biden's Venmo being compromised, even though, it was a secret account by using publicly available information. Similarly, wireless location data is sold by the various apps that we have on our phones. And even though the user identities are removed, it's very easy to use publicly available information to figure out where you are and what you're doing. Now, unfortunately, these app developers usually, collect and sell sensitive data, and this could potentially lead to controversies and important consequences for individual people. Now, this is what we see on the popular press, but I'm a researcher, so I want to kind of step back and tell you a little bit about how researchers think about these kinds of privacy compromises. The basic setup is thinking about two or more anonymized social networks, and the objective is to match the users in these two networks, essentially thinking about publicly and privately available information and how that can lead to privacy compromises. An important example of this was put forward about 15 years ago by Narayanan and Shmakatika, where they were able to put together Twitter, Flickr, and LiveJournal data to de-anonymize users. And some of the kind of algorithms that we see even to this day use seeding and propagation. So the idea is to look at these two or more social networks, the graphs of these social networks, identify a few seed nodes that can be clearly identified, and then propagate the seed mapping to de-anonymize users in the whole network. Now, the way, again, to think about these kinds of de-anonymization attacks is to think about social networks and possibly call logs being modeled as graphs. And a network graph represents user connectivity. For example, in this simplified diagram, I can think of the graph on the right-hand side where vertices are members of the network, edges represent friendship relations, labels of these vertices represent identities of the members. So we can also think about the edge attributes. We can think about a simple social network where you have connectivity or not. There's an edge or no edge. But we could also think about edges collecting a lot more information. For example, in a social network, you could have close friends, acquaintances, followers, each representing a different kind of edge. Or in call log networks, the frequency of the calls, call times, call lengths could be represented as multi-valued edges. And in this simple diagram, we represent different values of the edges with different colors. So then going back to these kinds of network de-anonymization attacks, we can think about two social network graphs. The first network has public identities. This is some data that you can collect publicly. The second one is the de-anonymized data that's sold by an app developer representing private identities. And the objective would be to de-anonymize the second network, figure out what the question marks are by using the similarity between public and privately available information. And this kind of actually turns out to be equivalent to a more abstract problem, which we call graph matching. So representing networks a little more, abstractly. Suppose we have two identical graphs. I'm sorry, the labels of the graphs don't show up that well, but the one on the left-hand side is G1, the one on the right-hand side is G2. G1 has vertex labels, G2 doesn't. So the question is, how do we restore labels for G2? When these two graphs are identical, this is a well-known mathematical problem that's called graph isomorphism, and people work on finding algorithms to match these graphs. But we can also think about graphs that are not the same but correlated. What if we have seeds, certain nodes whose identities we know in both graphs? These could be, for example, celebrities or politicians. What if the edges are multi-valued? Now, graph matching does not only come up in privacy contexts, but has a number of other applications ranging from biology, where we're interested in matching protein interaction networks of species, or image classification. Now, a simpler version of this graph matching problem, or the graph de-anonymization attack, is the database matching attack, where we have a simpler structure. So, what do I mean by that? We can think about databases containing micro-information shared and published routinely. These could be movie preferences, financial transactions data, location, health records, and basic privacy methods. Again, thinking about two graphs, say one is Rotten Tomatoes, the other one is the Netflix data, consists about anonymization, removing user identities, and obfuscation, changing some of the entries slightly so that, for example, Netflix data is still useful, but leaks less information about the users. Now, the question again is, are such methods really foolproof, and do they compromise privacy? In order to kind of talk about some of the well-known examples of this, I'm going to go back almost 2 decades to Netflix prize competition, where Netflix made available users movie ratings to develop better recommender systems, and the big prize was $1 million. Now, in order to kind of protect user identities and privacy, the identities were anonymized. Of course, we know that simply anonymization is not sufficient. And a landmark paper by, again, Narayanan and Shmatikov in 2008 showed that the Netflix prize database could be de-anonymized using publicly available IMDb data. And this made a big splash. There were lawsuits that followed, and kind of really brought this privacy issue at the forefront. Similarly, one can think about medical databases, where the first database consists of medical records that are anonymized. The second database is simple voter registration data in the United States. And Sweeney, again, almost two decades ago, showed that the matching these two databases leads to the anonymization and compromising privacy. Now, I said that kind of database matching can be thought of as graph matching. In fact, it's a simpler form of graph matching. So we can think of databases as these bipartite graphs where we list the rows on the left-hand side, columns on the right-hand side. So for the anonymized graph or database, we have the row identities removed. And again, the goal is to match these two graphs. So, one can think about in a more abstract fashion, two databases. One has row labels, the other one doesn't. How to restore the labels for the second database. What if the entries are not the same but correlated due to noise and obfuscation? What if in some time index databases, such as financial transactions data, location data, certain columns are missing or replicated? What if we have seeds where we know, some of the identities of people? Again, similar questions arise in database matching for privacy applications as well. Now, similar to graph matching, there are many other applications of database matching, not all of them malicious. They're heavily used in computer vision applications and biological applications. So having given you a kind of quick overview on the privacy compromises of these de-anonymization attacks and their kind of corresponding graph matching and database matching problems, I want to tell you a little bit about our perspective and where I come in. When we look at most of the work that's done on social network and database matching, this consists, the work consists of targeting specific data, with very successful outcomes, as we've seen. But a lot of the work lacks bounds and guarantees. Now, my perspective, and my background is in communications and information theory, where we want to understand foundations of networks. So I'm going to show you a little bit of our work and give you a flavor of what we've done, where we kind of approach the graph and database matching problem using tools from communications and information theory, leading to theoretical guarantees and new algorithms. In kind of simplified models, we're able to guarantee when matching can and cannot be done. And I'm going to argue that this way of looking at the problem creates new avenues for research and for protection of data. So we've looked at various problems, database matching and general graph matching, but I'm just going to give you a flavor looking at kind of a simple example of what we've done. So here again, we're thinking of the simplified database matching problem. The database on the right-hand side, D1 has user IDs. So I'm going to assume that there are m sub n users and there are n attributes for each user. The second graph, the second database, D2, is a similar database, but now the rows are permuted because of a different labeling or anonymization. We're going to say that the actual rows that have the same ID are matching, and these rows with matching IDs are correlated. So, for example, the medical data of a person and some of the other publicly available attributes are matching, whereas entries with different member IDs are independent. So our objective is to figure unpermute the second database or find the correct labeling that minimizes the error probability that matches as many users in these two databases as possible. So we're taking the perspective of the attacker in order to understand what can be done with respect to matching. So one can think about this problem as follows. So suppose I take a row from the second database, entry from the second database, and try to find the best match in the first database. Now, I'm going to argue that this is very similar to channel decoding used in communication systems. Now, you may be wondering, what is channel decoding and what does this have to do with communications? So let's kind of step back and think of a communications system, from its very basic principles. So anytime, you use your phone, your phone is communicating with the base station over a noisy channel. And this channel, the output of the channel Y, does not necessarily agree with its input X. So in order to protect information that goes through the channel, protect the information against this noise and distortions, we do processing at the transmitter side on your phone side called channel encoding. And we undo this processing at the base station side called channel decoding. And the main purpose of channel encoder is to add redundancy into the information so that it's protected against noise and variations in the channel. And this creates a structure in the signals that we send over the channel. So let me show you a very simple example of this. So suppose you want to send 2 bits of information over your channel. So it's going to be either 0, 0, 0, 1, 0, and 1, 1, but you know that the channel is going to introduce errors. So then you say, well, instead of sending the information just once, I'm going to repeat it, say, 2 times. So now a 0, 0 gets transmitted as 6 zeros. I'm sorry that kind of my matrix doesn't show up very nicely, but I hope I can get the idea across that repetition creates protection for data. So now we only have kind of the structure signals that we're sending over the channel. Now, the channel decoder uses this structure in order to correct for some of the errors. So, for example, suppose your channel output is the following. And what we're going to do is we're going to look at the channel output, compare it with possible bit sequences that could have been transmitted through the channel. And you'll see that the second row is closest to what I've received. So most probably the first bit was an error. And that allows me to estimate the correctly transmitted information. Now, this channel encoding and decoding is what all modern communication systems do. It's certainly what your kind of cell phone does. Now, how does this relate to database matching problem? Now, going back, I had these databases with structure and with correlation. And in order to find the label of one of the rows of the second database, I wanted to match it to one of the rows of the first database. And this kind of is very similar to the channel decoding principle that I showed you earlier. So this means that we can use the rich theory on channel codes to understand database matching and provide guarantees. And in particular, an important parameter here is the relationship of the number of rows and columns. So let's think about it like this. Suppose you have many users, so many columns and rows in this database, but only a few attributes, only a few columns. So then intuitively, it's very hard to distinguish these users. It's difficult to match, and it results in large database growth rate R. Similarly, if I have very few users, few rows, but a lot of columns, a lot of attributes, then it's kind of intuitively easy to distinguish between these users, easy to match, and it's a small R. So indeed, this database growth rate R, very much relates to whether we can match users or not. So a result that we've established a few years ago says that there's an intricate relationship between the database growth rate R and what I call the mutual information between the processes that generate these two databases. So you can think of it like this: if these two databases are highly correlated, then it's kind of very easy to match even very large databases. If they're less less correlated, then of course it's difficult to match. And this result quantifies, how much correlation and how big the databases, should be. Now we can kind of, taking this, simple database matching setup, we can now try to address, more complex social network structures, such as, ones that are represented in a graphical form. So, for example, we can think about random graphs, with seeds. So, if you remember, one of the important matching algorithms used seeds. So, some vertex labels in the de-anonymized graph are known, and the goal is to match the remaining ones. So the question is, how can we do that? And it turns out that we can have the problem, we can turn the problem into one similar to the one we've seen in database matching, where now we're only looking at the connections of the nodes in the graph to the seeds, not interconnection of all of the nodes in a graph. And it turns out, we can have an analogy to the database matching problem, where instead of user identities, we have unseeded vertices. Instead of attributes, we have seeded vertices, and can use similar ideas. With the twist that as we identify vertices in the second graph, label them, we can add them to the seed. Now, when we look at a problem of graph matching without seeds, it turns out to be a lot more complex. So I'm just going to kind of, show you this adjacency matrix where we look at connectivity of all the nodes. But unlike, our database matching problem, the moment you switch labels, you do a lot more than changing rows of this adjacency matrix. So we need more sophisticated tools. So maybe to conclude, I talked a little bit about database and graph matching problems with important privacy implications in social networks. There's a rich literature in system-level approach and algorithms for matching different graphs and databases, and this is indeed a big problem, societal and global problem. And I hope I've kind of been able to argue that, even a theorist like me can step back and use tools from a very different literature from communications to come up with new algorithms and conditions for success, helping us, design both algorithms in good uses of graph and database matching, but also protect our data. So, all in all, structure in these leaked, information over the web can be very useful for hackers. But we, as researchers and as technologists trying to protect that data, also have the tools to kind of to go beyond anonymization attacks. So I have a bunch of references. If you're really interested in digging, to the technical details. And with that, I'll conclude. Thank you so much for listening.
Thank you, Professor Erkip. There are some questions from our users. Are you ready?
Yes.
One question is about the evolution from 4G to 5G. Would that be improving our digital privacy, or are the privacy risks mainly at the application level?
Yeah, actually, kind of indeed going from from 4G to 5G and even to 6G, which is what we're currently talking about on the research and development side. I think the good news is that now privacy and also security risks are kind of being recognized. But maybe the bad news is that going forward, our networks are becoming much more desegregated. So, a lot of our network backbone is open source. The infrastructure is owned by different companies. The hardware is manufactured in different parts of the world. So while future generations of wireless networks do recognize and try to address privacy and security problems, there are also some new vulnerabilities.
There's another question here. The iPhone recently introduced a feature to prevent apps from tracking you. Is this a real and important step towards increased privacy? Or can the graph methods that you described easily recover the identity anyway?
Yeah, so I mean, that's certainly a welcome progress. As I showed in one of the popular press articles, simply buying this location data from the apps and correlating it with publicly available information can lead to significant compromises. Now, I don't know enough of Apple's feature to to really comment whether it will be foolproof. But of course, the data that apps sell is one piece of the puzzle. There's a lot more that we give away as we go on in our physical and digital lives.
We have a very attentive audience. So there's a question here. When trying to match a row from database 2 with database 1, each attribute should have a priority in order to prevent discrimination of the last attributes. Do you agree, or can you elaborate?
Yes. So kind of in the simplest setting, kind of we thought about these attributes are as being similar. But first, certainly there's a structure that we have in these databases, and the attributes, being correlated with one another. For example, if we're looking at medical data, age and prevalence of disease would certainly be correlated, and that, in fact, is an important factor in leaking information as well.
That
I
was
hope
the
that.
last question. Is there anything else I should ask you about, Professor Erkip?
Yeah. So, I think maybe what you should ask me is whether I think technology is enough to solve these privacy problems. So, I personally think that
Do you
we
think
as
technology is
technologists,
enough?
yeah, we as technologies can do a lot to prevent, privacy leakages. But I also do think that this has to go hand in hand, with a broader understanding of privacy risks, in the world, and with kind of regulation that supports, protecting users' privacy on the web.
And increase awareness among users, I think, as well.
Oh, definitely, definitely.
Thank you so much for joining the event and for contributing with so much. Thank you.
Yeah. Thank you so much for listening.